Module 1, The History of Science. Search for the Truth. True science begins to emerge from 600 BC to 500 AD. The ancient Egyptians, Mesopotamians, and Chinese, as well as other cultures of that time, continued to gather facts and record them. But they didn't go the next step in our definition of science. They didn't use those facts to come up with explanations of the natural world. This didn't occur until the 6th century before Christ, during the time of the Greek civilization. The men who are believed to be the world's first real scientists are Thales, Anaximander, and Anaximenes. These Greek scientists studied various areas of science. Thales, for example, studied the sky and tried to figure out if there was a way to explain how the planets and stars moved. He became so familiar with the planets' positions that he could correctly predict many planetary events before they happened. He even predicted when a solar eclipse would occur. This is when the moon moves between the Earth and the sun, blocking most of the sun from our view. Anaximander is thought to be one of Thales' students. He studied living organisms and tried to explain how humans came to be without referring to a creator. He believed that all life began in the sea, and at one time in history, humans were fish. This idea was not scientifically supported, but it resurfaced later on in history as the theory of evolution. We'll talk more about that theory later in this module. Anaximenes is believed to have worked at the same time in history as Anaximander. However, he studied air. He thought air was the most basic material in the natural world and thought that everything was made of it. So he believed thin air would warm up and form fire. Thick air became solid or liquid. Now, today we know that Anaximenes' ideas are incorrect, but he did try to explain all things in nature as being made of a single substance. And that led the Greeks to come up with one of their most important scientific ideas, the idea that all matter is made of atoms. This brings us to another Greek scientist by the name of Leucippus. He took Anaximenes' ideas and built on them. In fact, historians credit Leucippus as the one who proposed that all matter is made up of little units he called atoms. Thus, Leucippus is considered the father of atomic theory. Now, Leucippus had a student named Democritus. We know a lot about what Democritus did because many of his writings are well preserved. Democritus tried to illustrate his ideas about atoms using a visual picture. If you think of walking towards a sandy beach, you would first see the sand from a distance. It would look like a smooth, yellowish blanket. But as you get closer and closer to the beach, you might notice bumps and valleys in the sand. Yet the sand might still look like a solid material. When you finally reach the beach and look very closely at the sand, you see that it is not a solid blanket at all. In fact, it is made up of tiny grains of sand. Well, Democritus thought that all matter was like sand. It might appear to be solid, but that is because it is made up of very, very small particles we cannot see. These particles, called atoms, are tightly packed together in some substances and are loosely held together in others. He believed that is why substances behave differently from each other. Module 1, The History of Science. Search for the Truth. Experiment 1-1. Density in nature. We can explore how atoms make up everything by looking at how things behave in nature. And this is one way we can do that by doing this experiment. So what I have here is an empty jar, and I'm going to fill it 3/4 of the way with unpopped popcorn. Good right there. And then I have two objects. They're close in size. I've got a ping pong ball and a lead weight or a sinker. And I'm going to take the ping pong ball. Now, when you do this at home, just determine which one is heavier than the other, just so you know, and make a note in your notebook. You're going to notice obviously the sinker is heavier. But I'm going to take the ping pong ball and immerse it down, sink it down just below the surface of the popcorn kernel so you can't see it anymore. Don't jam it all the way down, but just below the surface. And then I'm going to take the sinker and put it right on top. So right now what we're seeing is a sinker floating on top of the popcorn kernels. Then you're going to take a lid and seal your container and swirl it, the whole container, very vigorously. And I want you to see what happens to both of those items. So here we go. And look what happened. We have the popcorn is really the same level, but the ping pong ball is on top of the popcorn and the sinker has disappeared. It sunk down into the popcorn. I'll explain what happens in the next section. Let's talk about what a hypothesis is. In this section, you should have completed your first experiment of the course. In the experiment, you were prompted to come up with a hypothesis by writing what you think will happen to the less dense ball. Although it sounds like a fancy, science-y term, a hypothesis is just a statement describing what you think will happen in an experiment. Say, for example, you are testing whether an ice cube will melt faster in cold water as compared to warm water. You have 2 glasses of water, one hot and one cold. You're instructed to drop an ice cube in each glass at the same time and watch to see which one melts faster. Of course, you probably already know what's going to happen. I suggested this as an example experiment so you can more easily follow what I mean. Now, your hypothesis would be something you write before you drop the ice cubes in the glasses. It's often best written as an if-then statement. So you might say, if I drop the ice cubes in the 2 glasses, then the cube in the hot water will melt faster than the cube in the cold water. Now, hypotheses do not always have to be in this if-then construction, but it is a good way to help you plan your question and answer to an experimental setup. What if your hypothesis is wrong? Is that a bad thing? No, an incorrect hypothesis doesn't mean the experiment was a bad one. It's a way of organizing your thoughts so that your experiment can test your statement to see if it's right. Either way, you come out of the process having learned something. In experiment 1-1, when you swirled the canister around, you should have noticed that the lead sinker sunk into the popcorn kernels and the ping pong ball floated to the top. Now think of this experiment in light of what we've been discussing about Democritus and how materials in nature have atoms that are more tightly packed than others. Remember the beach illustration. Democritus suggested that all things, including the sinker and the ping pong ball, are made up of individual particles called atoms, and the way those atoms are packed together determine how an object behaves. Even though both the sinker and the ping pong ball are about the same size, you probably have noticed that the lead sinker is heavier. That means its atoms are more closely packed together. There are more of them, densely packed into about the same space. Well, that means the sinker has greater density than the ball. It turns out that lower density substances always float on top of higher density substances. That's why the lead sinker sunk below the less dense popcorn and the ping pong ball floated to the top because it was even less dense than the popcorn kernels. Even liquids and gases are made up of atoms. Some materials have atoms tightly packed together, while others are loosely packed in comparison. So if you imagine every material to be made of little particles like sand grains, the more tightly packed together they are, the heavier the substance will be. Now, you cannot see the atoms, can you? But if you assume they exist, like Democritus suggested, the results of experiments like the one you just did are easy to understand. Scientists today still have not been able to see atoms, but as a result of lots and lots of experiments over hundreds of years, it is evident that all matter is made up of them. More experiments have revealed that each substance has unique ways the atoms are arranged, too. So Democritus was way ahead of his time. Even though he didn't get everything right, he did study materials and make lots of correct conclusions. And one of those is how atoms are in constant motion, even in a solid substance. Explore that in the next Explore More activity. Democritus got it right when he suggested that atoms were always in motion, even in solid material. In this Explore More, I'm going to take cold water and put it in one glass. And then I've got hot water, and I'm going to put it in a second glass. About the same height. There we go. And now we're going to see that these 2 glasses of water contain atoms that are moving. And I want you to see the movement by when we add a drop of food coloring in each. And you're going to notice that the hot water container actually is filled with atoms that are moving faster. So some atoms move faster than others, and we can see that in the fact that the atoms are bumping into those food coloring molecules, making them distribute more quickly than the atoms that are in the cold water moving more slowly. Let's get back to our tour of the history of science. I want to introduce you to 3 other notable Greek scientists. The first one is Aristotle. He was born a short time after Democritus died and contributed greatly to science. In fact, modern scientists call him the father of life sciences. Now, he did write lots of works on philosophy, mathematics, logic, and physics too. But his greatest studies involved living things. He was the first known scientist to come up with a way to classify animals and plants into categories based on their physical similarities. Aristotle was a respected scientist, but he did get some things wrong. As a matter of fact, one of his ideas stalled science for many years. Aristotle thought that some living organisms could pop up out of non-living material. This idea is called spontaneous generation. Spontaneous generation is the idea that living organisms can be spontaneously formed from non-living substances. One way that he came to this conclusion was by watching rotting meat after it was left out for a few days. It was observed that eventually young flies, or maggots, would appear on the meat. So they thought that if you left out non-living meat for a little while, it would actually transform into living maggots. Scientists today know that no matter how long you leave out meat, it will not turn into other living things. Thus, spontaneous generation is impossible. In fact, all science observations have shown us that life can only be formed by the reproduction of other living things. The incorrect idea of spontaneous generation should be a lesson to us as how science should not be done. You see, because Aristotle was a respected scientist who had greatly advanced science, people believed his wrong idea even though there was not any substantial support for it. It took over 2,000 years before scientists finally let go of it too. The next Greek scientist I want to cover is Archimedes. He lived about 100 years after Aristotle and moved science forward, particularly through using mathematics. He was able to apply math formulas to help explain why things happened the way they did. Finally, let's talk about Ptolemy. He was a Greek scientist who lived about 100 years after Christ. Ptolemy studied the heavens, describing planets and stars. He believed that the Earth was the center of the universe, and the planets and stars orbited around it in circular paths. Now, during Ptolemy's time, there was lots of evidence that seemed to support his Earth-centered ideas, and they became very popular. In fact, this arrangement with the stars and planets orbiting Earth is called the Ptolemaic system, or the geocentric system. Geo means Earth, so geocentric means Earth-centered. Now, this system was accepted to be true by scientists up to the 1600s. Today we know that it is an incorrect construct, but even after Ptolemy's death, although much of the data disagreed with Ptolemy's ideas, scientists still held on to the Ptolemaic system out of reverence to this great scientist. Plus, the Ptolemaic or geocentric system fit many scientists' preconceived ideas about how the universe should be arranged, with Earth in the center of everything. We can learn from these stories of Aristotle's spontaneous generation and Ptolemy's geocentric system. A scientist should not hang on to an idea just because it fits what he or she wants to happen, or because a brilliant scientist believes it. You will learn in the next few modules that science is built on data that is tested again and again. It is not dependent on what a person wants or believes.